All right, recording is rolling. So it is Tuesday, October 18th. You guys remember yesterday we were doing some conceptual questions with Kahoot on gravitation, and I want to take today and tomorrow to do as many textbook problems as I can do with you guys. So you guys remember I planned to use some problems from chapter 6 and chapter 7. Now the way your textbook is organized, the second half of chapter 6 is like circular motion, centripetal force, and chapter 7 is gravitation. And then if you take those two topics, put them together, you can also get orbits. Okay? So I've had time in class today to do the problems I assigned from chapter 6. So I'll do those with you guys. I'll just change the numbers so you guys have some extra practice to do. Okay? And then we'll save the chapter 7 problems for tomorrow. And so these are all going to be circular motion type problems. Okay? And you guys did a lab not too far back that going to relate to that. Right? Centripetal force, the whole deal. Okay? So let's do these problems. We should have time to do these 5 problems right here. Once I start, I assign to you guys. Right, so first one, number 61, car racing. A car, they told you the mass of the car. Real fast. In case you don't have this paper for any reason, maybe you're absent or something when I handed it out, got some extra copies right here. Extra copies right here. Right, an extra copy. Right, so chapter 6. Right. A car with this mass completes 1 lap every this many seconds around a track with this radius, a curvature. Right? So it's like a circular track. Right? The car moves at constant speed. Notice they said constant speed and not constant velocity, because the car does not have constant velocity, because it's on a curved path. Right? But constant speed. So if you're driving this car, can you guys see the speedometer needles just pointing at the same number over and over? That's constant speed, right? If it's changing direction. If it's changing direction, then there must be a net force on it called centripetal force that's causing an acceleration. Okay? And those are the 2 questions. What is the acceleration of the car, and what force must be exerted on the car to cause that acceleration? Right? So zoom out. Let's see here. 62. Sorry, 61. Oops, 61. Right. Let's get a circular racetrack. Ourselves a car here. Okay. Now, a question they did not ask, but it'd be a really helpful middle step, is to figure out, well, what is the speed of this car? Right. So I'll call that V, right? This V for speed in this case, right? Okay. Now, as this car is going around, right? Now, you guys know that there. The first question is, what is the acceleration of the car? You guys know that it's not linear acceleration. In other words, it's not tangential acceleration. So if you think back a couple months in this class, like you guys remember these guys, right? It's not referring to this, because the car is not speeding up to slow down. Right? The guy's not slamming on the gas pedal to speed up. He's also not slamming on the brake to so just stop. So none of this stuff is going on. Okay? The acceleration we're talking about is a centripetal acceleration caused by a centripetal force. And what force? Which direction should I draw the force? We're up here in a helicopter looking down on this car, right? Right. So if this car is always making a left-hand turn, you guys see a constant left-hand turn, like always turn left. Okay. What is the direction of the force from this point of view? Yeah, it's always, there you go. Right? It's always directed towards the center of the circle, right? That right there is your centripetal force. Okay? Now the question is ambiguous as to exactly what's causing that force. So it's probably one of 2 things. It's either friction. I'll go ahead and label it friction force. That would be true on a flat track. If the track is completely flat, that would be the only force that would allow that to happen. Right? The other possibility, though, is that maybe the track is actually banked. Right? What if it's like turned up at some angle? Right? In that case, it could be some component of the normal force. Right? So one or the other. But that is the direction of the force, so that as the car tries to move forward, it's also deflected leftward onto that curved path. Okay. But we need some values. They told you the mass of the car. I'm going to use a different mass. I'm going to use this many kilograms car. Okay. They told you the radius of curvature. I may come up with my own radius of curvature. Maybe I'll go this many meters. Okay. So it's like from the center of the track. Radius of curvature right there. Okay. And they also told you the time period to make 1 complete loop. So I'll come up with my own number. So 70 seconds, right? So my numbers are different than your numbers, but it's the same, it's gonna be the same process. Okay? So centripetal acceleration and centripetal force. Well, first I have to solve for this V. Right? So let's solve for it the same way that you guys did for your lab, right? Isn't speed equal to distance over time? Looks like that. Okay. And hey, isn't the distance that the car makes one complete trip around equal to the circumference of a circle? What's the formula for circumference? 2 pi r, right? And it does that distance in the amount of time of one time period, right? Can we use that expression to figure out the speed of the car? Right? So I'll do my numbers. So I have a racetrack with this radius curvature, and it takes this car this many seconds to go around once. So boom, boom. Now I can figure out what's the speed of the car, right? That distance in that time. And I'm looking at this many meters per second. Literally 1984. Right? So there's the
Oh wait, literally.
somebody got make jokes myself up here. Sometimes somebody gets it. Yeah.
You know that meme?
Uh,
I see it all the time on Discord.
So
I was like,
we need centripetal acceleration and centripetal force, right? Now, some formulas you could use for that. Centripetal acceleration. Let's start with the one that we're not going to use, omega squared times r. Now, that's a pretty handy, we could use that. We could solve it this way. And that's a more useful formula for like turntables and O'Neill cylinders. Okay? But the easier version that we're going to actually apply is linear speed squared divided by radius of curvature. We can do that, right? Okay. So yeah, well, let's feed that in, the numbers into this expression to figure this out, because we know how fast the car is going. Okay. And we know radius of curvature. Okay. So this is the number on my calculator screen. Okay. Now, since this is a physics class, okay, this number has units attached to it. And what are the units? You guys were thinking meters per second squared, right? Because it's an acceleration, right? Okay. And well, all the numbers that fed into it were all in base SI units. We got meters per second, we got meters per second squared. Also think about what does the context of that number mean? Now, I know I just made up some numbers on the fly that were different from your numbers, right? But okay. You guys up here, for context, isn't the gravity field that we're in right now, like if I drop this pen, what you guys are looking at, isn't it free falling? Let's call it about 10 meters per second squared it's picking up. Hey, look at this compared to this. Isn't this number a little bit more than half of this? Okay, so if you're inside this car on this track going at this speed, what that means is you would feel, it would feel like there's a sideways force that's a little bit more than half of your own weight. You see it? Like more than half a G, right? That's pulling you to the side. Okay, so that's an interesting context. This is the answer to question A. Okay. Now question B says, what's the actual force that's causing that? Okay. So you could have done this. Centripetal force is mv squared over r. Okay. We just plug it in. Okay. We've already done this part though. Okay. We just figured that out. That's this. Okay. Centripetal force is mass times centripetal acceleration. Okay. That sure does look a lot like Newton's second law of motion, because it is. So I'm going to plug in my car right here, how many kilograms that is. You guys have a different car. Okay. And this centripetal acceleration. Okay. And because these are in base SI units, kilograms and meters and seconds, what we'll do, okay, then you guys can know the unit for force. And that's 7,000 what? What's the unit? Newtons. Yeah, it has to be newtons. Right? Or if you like, yeah, I guess you could even say this. 7.2 what? Kilonewtons? Or times 10 to the third newtons or power. Okay. guys good with the number 61? Oh, yeah.
Can you show the other page?
Yeah. All right, so run over that one more time. They gave me some values, right? Mass, radius, curvature, and the time to go around one, so the time period. Okay. So this was kind of a two-part problem. The first part was to figure out, well, how fast is the car actually going? Right? What is its instantaneous speed? Right? And then once you get that, then you can feed that into, well, something that looks like it came from out of your lab. Right? You know, whether you do the force version or the acceleration version, right? There's different, you know, the mass. You can multiply it by the mass, go from one to the other. Okay, to get either the centripetal acceleration, which is, you know, kind of like how many G's, you can think of it that way. Okay, you can divide by this, looks like a little over half a G. Okay, or the resulting force might be the friction force from the road. All right, number 62. Right. Actually, in retrospect, I wish I hadn't assigned both of these because these are almost the same problem. Okay. But number 62, hammer throw. So we're up here in a helicopter watching the sky with a hammer, rope, right? He's going around with some speed. Right? They look tangential velocity, like speed. Right? They told you the mass of the hammer, the radius of curvature, and the time period. And they say, what's the centripetal acceleration and what's the tension in the chain? You guys see how like that's mathematically identical to what we just did? Right? Same given values, same everything. Right? You know, it's a tension instead of maybe a friction force or something. Right? I actually will throw one little twist on the end where it could be slightly different problem, but it's almost the same thing. So actually, a good thing to do is see if you guys can like stay a step ahead of me because we've essentially solved this one. Right? So if you got the last problem, pretty good. See if you guys can beat me to the answer with this one. Right? I'm going to change the numbers a little bit, but not very much. So maybe I'll have a hammer that's a little bit heavier. I'll have a radius of curvature that's, let's say, a little bit bigger. And maybe I'll have a time interval that's a little bit longer. Right? Whoops, that's seconds. Oops. Right. So I changed the numbers from the book numbers, but not by a whole lot. So my final answer should be kind of close to your final answers. Okay. Right, so I remember what we did before is, well, we said the speed would be the distance, which is circumference, divided by the time period. So here's the radius of curvature, multiplied by 2 pi, you can get the circumference. And that all happened in this many seconds. Okay, so now we can get the instantaneous speed. Okay? So if you like point a radar gun at the hammer at any point, how fast is it going? Okay, and that's okay. So I'm getting number of meters per second is what it's going to be. Right? So many meters per second. Okay, then you can use that number, right, that speed, to calculate centripetal force and centripetal acceleration, which have pretty similar looking formulas. The centripetal acceleration is just v squared over r. So this many meters per second, square that, divide by radius of curvature. I'm getting okay, that's way too precise, but you guys get the idea. Oh, hey, suppose I rounded that down a little bit to call it about 60 meters per second. 60, or sorry, meters per second squared. 60 meters per second squared. Guys, how many G's would that be? 6. Yeah. Right. Here, little dimensional analysis. And set up some railroad tracks right here. Say every 10 meters per second squared, it's like 1 G. So you definitely see it now, right? You guys see about 6 G's. So if you were a ladybug and you like, no, I'm gonna land on this hammer right here, and the guy starts wheeling around, right? You would feel 6 times as heavy, wouldn't you? Right? Because that's centripetal force. So centripetal force. Okay. Well, right. So let's do mv squared over r. Okay. And the v squared over r bit we already solved for. That's this right here. Right. Okay, so I need the mass of the hammer, which is this many kilograms, times v squared over r came out to be this many meters per second squared. That's what they have kilograms and meters in seconds. It's going to give me so many newtons. Let's see. Okay. So looking at call it 496 newtons. Okay. Now that's centripetal force. Now, if you call that the tension in the rope, then that would actually that'd be pretty close enough. But here's where I want to take this one extra step just for fun. Okay? You guys get that so far? Okay. So here's where this kind of deviates from the last question. If there's a way to do that. Okay. How many guys were thinking back when you were doing this lab, which looks a lot like what we just solved, okay, that this circle right here isn't actually a perfect horizontal circle? This string is not exactly horizontal. It's actually a shallow cone. How many guys were thinking that? Right? Because this Play-Doh canister doesn't just have inertia. It also has like a weight pulling it down that we ignore during the lab, which is okay because it ends up being a very tiny effect on the whole process. But let's see how tiny of an effect that is. We're about to find out. See, it's 496 newtons is strictly horizontal, like pulling the hammer in. So let's get a side view of this. Here's your hammer, it's something like this. Right? And the rope actually is not exactly horizontal, so I'm not gonna draw that way. The rope is like pulling kind of up into, right? So here's the sky. Okay, it's like pulling, okay, things go around. Okay? And this hammer has like two forces on it. It's got the tension pulling up and to the left, and it's also got the weight pulling straight down. Okay? And if you take this tension and break it into components, the vertical component must balance out with the weight. Here's the weight of the hammer. Okay? And the horizontal component actually is the centripetal force that we just solved for. Okay? Okay. Guys think of that? We just found that this number here, we're going to do centripetal force, which is this component, actually pulling us into a circle. I'll just go around like the circle. I got 496 newtons, right? And the question from the book was, what's the tension of the rope? Now, if you said 496 to call it a day, again, it's so close to the answer, it's probably fine enough, right? But what would it be if you actually included the mass, like the weight of the hammer? Right? So remember, I have a mass of 8 kilograms. This costs about 10 meters per second squared. Would that be like 80 Newton weight, 80 newtons, right? So this tension pulling up into the left, well, it must be pulling upward with also 80 newtons to balance out the weight pulling down, right? Okay. And the actual tension would be greater than the centripetal force. Not much greater, but a little bit greater because of that triangle. Okay. Can you guys do Pythagorean theorem between these two? Okay. So let's see what the actual tension is. Force tension is. Well, it's Pythagorean theorem. So what's the square root of 496 squared plus 80 squared? Pythagorean theorem. Okay. I'm getting 502 newtons. So there you go. Okay. So if you just did mv squared over r, you get 496. If you go one more step and do Pythagorean theorem, say, well, the hammer also has a weight, right? Then is it being, you guys see that's like so close, so close. Okay. What is 496 compared to 502? It's like 99%. Okay, so it's rounded even less than this number's rounded. Guys got that? Okay. 65. Friction provides the force needed for a car to travel on a flat circular track. Hey, it's kind of like what we were thinking of before, right? But this problem's a little bit more involved, though. It makes it a little bit more fun. What is the maximum speed that the car can safely travel if the radius of the track is so many meters and the coefficient of friction is, okay, they give you coefficient of friction. Okay? Now, you guys ever drive on the interstate? You go on the off ramp and it goes on like a curve, right? And there's a speed limit sign that says, don't go faster than this, right? Maybe kind of push it and it goes, ooh, feels like I'm about to like fly off the road, right? Now that's because of the inertia of the car and you're not like on a curved path, right? No, part of what helps you stay on is the fact that the track is banked. We're going to ignore that and just because they said a flat road, right? A flat circular track. Okay? So friction would be the only force that would allow you to stay on that track. Okay? So let's look at the 65. So I want to get two views of this car. One is helicopter view, an aerial view. So we're above, looking on this track. Okay. So here's this car. This car going this way, let's say counterclockwise. Right? So it has some V, some speed. Okay? And from above, I know that there is a centripetal force that's acting as there's a friction force that's acting as the centripetal force. Okay? This track has some radius, call it R. Okay, so we got that, right? But what else we're going to need is, guys, this friction force, isn't friction force related to the normal force of the car, right? Which is related to the weight. In fact, the normal force is equal to the weight as long as it's a flat track, which we do have here. So the other view I want to give this car is like from behind. Suppose we're like behind this car, okay? And look at this car, and from behind it looks something like this. Right? It's got some tail lights. Right? It's got some wheels going on here. It's got a license plate. Right? That's this car from behind. Okay? And let's make a free body diagram on this car looking at it from behind, because this force is the friction force, centripetal force, right? So we got that. That's like here, FFR. Right? But from this point of view, we can also see the other two forces, which are its weight and the normal force, which is equivalent to the weight. Isn't that true? Okay. So like the aerial view, we can't see these two because they're like into and out of the page, right? So, they gave you some numbers. Notice they did not give you the mass of the car. They told you the radius of the track, which I'm going to change a little bit. Let me just call it an even 100 meters. Right? For you guys, it was 80 meters. Okay. They also gave you the coefficient of friction, and they gave you guys 0.4 as the coefficient of friction. Now, guys, coefficient of friction of 0.4, isn't that friction force compared to normal force, right? Which should be like 40%. So if you drew your free body diagram exactly to scale, then your friction force could be up to 40% of the normal force, right? I mean, it could be less than that, but it can only go up to that value, right? Talking about static friction. Okay? Now, for me, looks like my friction force is a little bit less than the normal force, but not very much less than. Maybe I'll call my coefficient of friction like 0.8. How about that? It's a little bit more realistic between the tires and the asphalt. Okay? Now, 0.4, maybe that could be the case if it's been raining outside, something like that. But I've got in, this could be like up to 80% of this. Okay, that's what that is. Okay. Okay. And you guys also know, they did not explicitly give you this, but you guys know that gravity could be about 10 meters per second squared, right? And they never gave you the mass of the car, which is maybe a hint that it's going to cancel out at some point. Okay. Right. So that's what I'm thinking. I'm thinking that the centripetal force is provided only by the friction force. Is that true? Right. This force is the centripetal force, right?
That does make sense.
Now, you guys know an expression for centripetal force, which is what? It's on that poster closer to the projection.
Mass times velocity squared over radius.
There you go. mv squared over r. Okay, just like that. Okay. Okay, mass of the car. Well, we don't have that. Ooh, that's a bad sign, but that's okay. 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 Ooh, v. That was the question. How fast can the car go? So at the end of the day, we are solving for that v, right? Hey, in race to the track, they gave us that. Let's go look at normal force. Isn't that coefficient of friction times the normal force? Coefficient of friction times the normal force. And the normal force.
That's how mass cancels out.
Ah, yeah, you see it, right? Because it's equivalent to the weight on a flat track. Okay, so we do one more substitution. mv squared over r is equal to mu times mg. All right, and this is where the mass of the car cancels out. So it doesn't matter what car you have or if you loaded it up with groceries or not, right? As long as the tires are the same from car to car, right? If you had different cars, as long as the tires are the same. There you go. Okay. You know what? We're really close to just solving this in terms of variables. So let's just go ahead and do that. There's two algebra steps. Can you guys cross multiply r and take the square root?
Yeah.
So the speed of the car would be the square root of coefficient of friction times gravity field of the planet times the radius of curvature. Okay. So let's plug in some numbers. No, this is like V max, right? V max. We got 0.80, 10 meters per second squared, and I'm going 100 meters radius. Okay, you guys have different numbers. Square root 0.8 by 10 by 100. Okay. My car can go up to 28 meters per second. Okay. So if my car is going 28 meters per second around that curve, it's gonna be okay, but it's really pushing it. Like it's right up to the breaking point. Right? If it goes 29 meters per second, well, that's it. It's gonna break friction and slide off. Okay. Like tangent to its motion, just in a straight line. Okay. Alright, so while you guys are digesting that, like, recap that problem. Okay. So this car's going around a curve, and the question was how fast can the car go? Okay. And they told you like the size of the curve and also the coefficient of friction between the tires and the road. Okay. And it turns out that's all you need, okay, as long as you know what planet you're on. Okay. So I said the centripetal force is provided by the friction. Okay. Overhead, it looks like that. From behind, it looks like that. Okay. And then we made some substitutions because you guys know from your lab, this is an expression for centripetal force, which has the V that we're ultimately solving for. And friction force, well, that's coefficient of friction times the normal force. Normal force was equivalent to the weight. And at this point, the math cancels out. Okay. We went ahead and solved it in terms of variables because we were so close to doing that anyway. Right. So this expression works for everybody. Right. Then just plug in the numbers that they gave you. Point, point, point. Okay. How fast can car go? Okay. Okay, so we got 2 more to go. Number 66. A carnival clown rides a motorcycle down a ramp around a vertical loop. If the loop has the radius, okay, so this radial size, what is the slowest speed that the rider can have on top of the loop to without falling off? Okay. And they gave you guys a hint. It says the normal force goes to 0 at that at the minimum speed. Okay. So I've been changed this a little bit to call it a roller coaster, or you know what else I can call this? Okay. All right. Let me do you guys a live demo here. Got a cup full of water. Ooh, it's gonna be a fun demo, right? Got some water in a cup. Okay. Oh, it's in a stream. Okay. Hey, do you guys think there's a way I could tip this cup upside down without the water spilling out? Ah, yeah, it's spinning, right? It's spinning. Okay. So if you're watching this on video at home, I'm just gonna rotate this in a vertical loop. Oh, look at that. The water stays in the cup. Right, water stays in the cup. Okay. Hey, what if I slow this down?
It's gonna start spilling.
Gonna start spilling at some point. So like there's some minimum speed, right? Right. It has to be moving. There's like some place where like the water actually would spill out. Okay, so it did. Water's still in the cup, so we're all good. Ah,
You know it spills.
yeah, it's okay. All right, oops. All right, I'll live. Just let me let you. So this looks like need more paper. Right, so whether we're talking about like a roller coaster or a guy on a motorcycle going on a vertical loop or water in a cup, right? It's going to be all the same physics at this point. Right? So same idea, right? So maybe I'll draw a roller coaster because roller coaster might come back a few weeks from now. Right? We're doing conservation of energy like roller coasters, right? So we got ourselves a vertical loop and on from there. Okay. Right. And at some point, you know, the guy that riding a motorcycle or maybe a roller coaster is going to be like very top. And that's where like the critical point it has to get past. Okay, so we're going to give this thing some speed. Call this V, right? There's some minimum speed because if it has 0 speed, it's just going to like fall off the track, right? There's some minimum speed it needs to get around that vertical loop. Okay. Now, before I dive into that physics exactly, okay, do you want to make a like an engineering point? Right? Yeah, look, water still off. Right? But take a look at this roller coaster. Now, when you guys actually go to theme parks and you actually see roller coasters, you guys see how that shape is different from the one I drew? Right? See, it's like a, it's not actually a circle. See, it's like an upside down teardrop. I said teardrop shape. Okay. Versus I drew one that looks more like a circle because this is, you know, kind of a starting physics type class, right? Now, when people were making the first vertical loop roller coasters about 100 some years ago, right, they actually did start making them just like circles like this, right? But then they realized those were causing a lot of, well, there's some problems with that. Okay.
People fell off the top.
Well, you can send them around fast enough where people wouldn't fall off. Okay. But think about what this would feel like. Right? Suppose you're on a straight track, and then suddenly you hit like the circle, and you're like, bam, you're in the circle, right? Okay. What would that feel like? Okay. Like if you're on a straight track, don't you feel a lot like in this room or going along the interstate constant speed? Okay. But when you hit that circle and suddenly, like, bam, you're on a circular path. Okay. Doesn't that centripetal force just like bam hit you all at once? Or, of course, it's normal force from the track causing that, but you guys get the idea, right? Okay. That's why you want a teardrop shape, because here's what a teardrop does. Okay. Teardrop, it's like it gradually goes into like the loop, right? Now you could do the same type calculations, but here would be your radius of curvature, right? It would be like at the top there's a tiny circle, but when you're like right here, you get kind of a medium circle, and then like here you get a very large circle. Right? Okay, so you go from a large to medium to a small circle. Okay, so it's like gradual buildup. Okay. But we're gonna do just real basic, just assume like it's just a circle. Okay, so just simplify this a little bit. Same idea. Okay. And let's think about what forces are or could be on. I'm just gonna call it a roller coaster. Say at that point. But if you want to replace it with a cup full of water, it's the same idea. Now, there's definitely some weight pulling down on this point, right? So I'll go ahead and label mg for weight. Right? Now, suppose it goes around with sufficient speed. Sufficient speed. Is the track also pushing down on it at the same time? It goes around plenty of speed. Okay. I think
Yeah.
so.
That's normal force, right?
Yeah, that is normal force. F sub n, right? Now maybe it's bigger than the weight. I drew it smaller than the weight. Maybe single weight. It depends how fast. If it goes crazy fast, suppose it goes like a centrifuge. Do you think it's probably going to be more than the weight? Okay, so this depends on how fast it's going. Hey, now what about if it just barely gets around? Barely gets around. What do you think happens to the force from the track just at that moment? It approaches what? 0. So this is going to approach 0, isn't it? Right? Just for the case of like minimum speed, just barely gets around, barely gets, right? So the centripetal force in general is the sum of the weight and the normal force from the track. Right? They're both conspiring together to keep this roller coaster car on this curved path. Right? Some of those is acting as collectively as the centripetal force. Okay? But in the case of like minimum speed, just barely gets around, this approaches 0 newtons. So we're going to call it 0 newtons. Centripetal force is your mv squared over radius of curvature. Right. And in this case, we're saying it's only provided by the weight. Only the weight allows it to just get around. Okay. Hey, what cancels out at this point? Yeah, the mass of the roller coaster. So it doesn't matter if it's an empty coaster or if it's filled with passengers. The speed you need to get around is the same regardless. It doesn't matter how massive it is. Okay. Side thought, you guys sort of saw a version of this. Isn't this also a similar idea to orbital speed? Sort of, great. But when we were solving for speed of satellites, we didn't use mg for the weight. We used gmm over r squared, which is the more universal way. See, like mg with lowercase g is okay at the surface of a planet because this g consolidates a bunch of those variables, but it's the same idea, right? Same thing with the satellite, though, is that the mass canceled out. Okay. So next step, actually, can you guys do 2 algebra steps here? Cross multiply the r and then take the square root. So this here, v squared is g times r. Therefore, v is equal to the square root of gr. Okay. Now, again, that's if the normal force is 0. So this is really a minimum speed, okay, which is what they asked for anyway. Okay. Oh, and look what we just did again. We just solved in terms of variables, okay, which means that everybody can get the answer regardless of the size of your roller coaster circle. Hey, regardless of what planet you put it on, too, you could take this roller coaster to the moon and just solve this very quickly, too, couldn't you? So, amen. Okay. I'm just gonna make up some number here. Well, let's go 10 meters per second squared. Suppose I have a radius of curvature of 25 meters. How about that? So we got that'd be 15.8 meters per second. Or how about this? This cup full of water just has slightly less water in it. This string, I'm going to estimate the length of the string is about 40 centimeters long. I wonder how fast that cup had to be going right at the top. 40 centimeters. That 10 meters per second squared gravity times 0.40 meters about. There's a 40 centimeter radius. That's 0.4 meters, right? It's all base SI units. So square root of 10 times 0.4 is 4. That'd be 2 meters per second. Okay? So that cup had to be going 2 meters per second at the top of that vertical loop. Okay? If it went any slower, the water would fall out. Okay?
You spun that 10 meters per second? I mean, 2 meters per second, not 10.
Yeah, it had to be going like 2 meters per second at the top. Yeah, so it was going like 1.5 and the water would just fall out.
All right.
Okay. Or the tension would also go slack and it wouldn't make a circle even. All right. All right, one problem to go. All right, we're doing all right. So number 74, we got early skeptics of the idea of a rotating Earth said that the fast spin of the Earth would throw people off at the equator into space, okay? Which, you don't have physics to be able to approach this problem I guess that's sort of possible if you're spinning fast enough, right? It's going, throw people off, right? Just staying at the equator. Right? So we're about to do the math to check this idea, right? To test it. Like, I wonder how close that is to happening or what. So they gave you the radius of the Earth. Notice they gave you in kilometers, right? So when you plug, when you feed these numbers into equations, you have to convert that to meters first, right? You need meters. Then show why this idea is wrong by calculating, right? And then there's like 4 parts here. So there's a particular way they're wrong with the story, but we'll follow their way and then we'll see what we can get out of this. 74. Okay. So let's get a picture of the, zoom out here. We got okay. Picture of the Earth. Okay. Here's the equator. All right. Poles, right, hold yeah, right? Okay. Here's the, this could be the radius of the Earth, okay, which is a fixed value. Let's call it capital R. Okay. And then there's like somebody standing here at the equator, okay, and they have some tangential velocity, tangential speed, call that V. Okay. Just like that. Okay. So, oh, and they did tell you the mass of the person. So I'll label that M for mass. Okay. They went through force and so we know the mass of the person, they said 97 kilograms, so we'll work with that later. The radius of the Earth, they said 6.38 times 10 to the 3 kilometers, but we're not going to feed that into the calculator. We're going to feed in 6.38 times 10 to the how many meters? 6, right? Kilometers to meters is like times 1,000. That's 3 decimal places, right? That's the number we want in the math. Okay, so the speed of the person at the equator. So what's well, I guess we're going to go with angular speed or linear speed. So you can go either way. I have linear speed drawn here. Hey, how do you guys think we could solve this? The linear speed. Do you know anything about the speed of the Earth one way or another? Do you know its angular speed? Can you guys think of a way to get its angular speed? Okay. Back up, real big picture here. You guys remember this turntable? You guys remember these 3 Roosevelts all have the same angular speed? They're all doing the same turns per time. Hey, suppose we were like from above looking down on the North Pole. Like here's a like Santa Roosevelt, okay, doing out New Deal programs. Okay? And then as you go down, here's like the equator down here, right? Right? But they're all making the same turns per time. Is that like 1 revolution every 24 hours? Ah, that would be for the Earth, wouldn't it? 1 revolution every 24 hours. You guys looking at time lapse. Okay? Okay. But then linear speed, it'd be different. Like it'd be 0 meters per second for like Santa Roosevelt. Okay? And then as you go down close to the equator, you know, faster, faster, faster. Okay? So let's calculate the angular speed in like radians per second, because radians per second is a number we can do some calculations with. Okay. Well, I can think that angular speed of the Earth is 1 revolution every 24 hours. Wouldn't that be true? 1 revolution every 24 hours. Okay. Now, again, revolutions per hour, that's not a number that I can do math with, but I can convert this to radians per second. Let's set up some railroad tracks, convert to radians per second. I think we can do that, right? So 1 revolution, how many radians is that equal to?
That's equal to 2 pi.
2 pi. Yeah, 2 pi radians. Okay, so now we have radians per hour. We want radians per second to be able to do some math. Is 1 hour 60 minutes and 1 minute 60 seconds? Radians per second. Okay. So what's 2 pi divided by open parenthesis 24 by 60 by 60? Okay. So here is the angular velocity of the Earth. 0.00007272 radians per second. Or if you like, you call it 7.272 times 10 to the negative 5 radians per second. Okay. Or if you like, times 180 over pi. That's the same thing as 0.0042 degrees per second, which we're definitely not going to use, but just an interesting idea. Right? Tiny sliver of a degree every second, which of course is ridiculous, but it takes 1 day to turn around once. Right? Okay. So we're gonna use one. So we got the angular speed. That could actually answer the question. But suppose you want linear speed. Isn't linear speed equal to angular speed times your radial distance from the center? So let's plug in 7.272 times 10 to the -5, that's radians per second. And we got a radius of 6.38 times 10 to the 6, because that's meters. The beats in right there. Okay. This would give us the speed in, say, meters per second. Well, it's meters per radian, it's radians per second, give you meters per second. So it's 0.7272, 6.38 times 10 to the 6. Okay, yeah. So I'm looking at 464 meters per second. Okay. This is for standing on the equator. So if you go down to Ecuador, right? That is your speed, say, relative to the axis of Earth. Okay. We're ignoring the Earth, going around the sun. We're just focused on the Earth spinning itself. So we did that. Okay. By the way, that's about 1,000 miles an hour. It's pretty close to 1,000 miles an hour. Okay. Of course, we don't feel that because we don't feel speeds. That is the answer to question A. Okay. Question B. What is the force needed to accelerate a person in a circle? Okay. So question B. Suppose we're watch this person on the equator. Okay. So kind of exaggerated much, right? And they're moving around in the circle. Okay. Do you guys think that centripetal force would be mv squared over r? You know what else you could do? You could have done this m times omega squared times r. You would get the exact same answer. So you could do either approach. Right, here's omega, here's v. Okay. Let me just pick this one. Okay, we'll run with that. So I got 97 kilograms, that's from before. I got 464 meters per second. Square that speed, divide by 6.38 million meters. Okay, we've got about to get the centripetal force. 97 times 464 squared divided by, yeah, we got 3.27 newtons. 3.27 newtons. Okay, that's the answer to question B. Okay. It's 3 newtons. Okay. 500 grams weighs about 5 newtons. So the amount of force that 97 kilograms, by the way, is, I think it's heavier than probably anybody in this room. That's pretty big mass, big weight. So you need less than the weight of this to hold down a pretty heavy person, right? Without them flying off the face of the earth due to its spinning. Right? Question C: what is the weight of the person? Okay, which is really just a setup for question D. So C, you guys know weight is equal to mg. So we got 97 kilograms, 10 meters per second squared. Is that 970 newtons? That'd be your weight, right? Okay, and then question D, what's the normal force of the earth on the person? Okay, their apparent weight. So if this person steps on a scale, you guys know when you step on a scale, that scale actually reads the support force from the surface, not the actual gravitational force on you, although those are really close to each other. We've been assuming they've been the same all along, but now we're considering the earth is rotating. That's not exactly true. That's just pretty close to true. Just put this person on a curved surface standing on a scale, right? And there's 2 forces that, again, up until about last week, we've been saying are equal, but that's not exactly true. They aren't exactly equal. Okay. So this person has a weight that's pulling straight down, mg, and that number is 970 newtons. Right? And this person has a normal force that's actually not as much. So I've drawn this greatly exaggerated. Okay. But the difference between these two would have to be the net force, which is the centripetal force. So let me make a little expression down here. So centripetal force equals the sum of forces, which is that minus that, because they're opposite directions, right? So your weight minus your normal force. Okay. Centripetal force, did we just calculate that to be like this value? I'm going to round this down a little bit. Is it okay if I call it about 3 newtons? Is that okay? Like 3 newtons, right? Right, so I'm gonna round this to 3 newtons. So 3 newtons is the difference between the weight down and the normal force acting up. See if you rearrange this, you're gonna get the normal force is 967 about newtons. Okay, that's this right here, 967 newtons. Okay, so when you step on a scale, if this guy's on the equator, the scale's gonna say 967 newtons of weight. But the actual gravity force is a tiny bit more than that, actually 970. Okay. Last question. Okay, so the net force of 3 newtons is like what allows them to stay on a curved path, right, going around. Last question is, I wonder what percentage that is. Now, this is only true on the equator, although in Florida, like so many degrees up, this is pretty close to being on the equator. Like, you know, you have to do some trigonometry, but that aside. What is 967 compared to 970? Okay, so that divided by that. The ratio of those two forces is 99.7%. Okay, so the Earth spinning, even if you're on the equator where this effect would be most pronounced, the Earth spinning only reduces your weight by less than 0.5%. Okay, you guys see that? Less than 0.5%. All right. And that is a good pause point. Actually, I'm gonna upload this one to Google Classroom. I think I got the best take for this one. All right, so that's a good pause point. All right, and tomorrow we'll do chapter 7 problems.